All right, today we're jumping into a theory that is so out there, so radical, it's basically proposing we rewrite the foundations of mathematics itself to create a whole new language for physical reality. This is Topos theory.
You know, at the very heart of this is a fundamental choice. It's a tale of two worlds. On one hand, you've got the smooth world of classical physics, calculus, continuity, the idea of the infinitesimal. But on the other, you have this discrete world, a reality built from computational steps, kind of like pixels on a screen. Well, Topos theory makes a pretty bold claim. It says reality is fundamentally discrete, and it is way past time our math caught up to that fact.
So here's our roadmap for how we're going to unpack this thing. First, we'll look at the big problem with context in classical math. Then, we're going to meet the proposed solution, this idea of a universe literally made of tokens. After that, we'll dive right into the technical core with something called the W-field dictionary and see how it completely redefines what truth and emergence even are. And finally, we'll get a handle on the brand new grammar for reality that this all offers.
Okay, Section 1, a theory of context. Now, classical mathematics, it already has an incredibly powerful tool for handling context. It's called Topos theory, and you can think of it like a brilliant, beautiful castle, but it's a castle that's just floating in the air.
And this quote from the source material just hits the nail on the head. The result is beautiful mathematics that stops one layer shy of ontology. So what does ontology actually mean here? Well, it's the study of what is, what actually exists. The classical theory is elegant, for sure, but it's pure abstraction. It describes relationships, but it doesn't describe a world that you can physically build. It's a blueprint with no ground to build on.
So let's get into Section 2, a universe of tokens. How do we anchor that floating castle? How do we bring it down to Earth? Well, the theory proposes a pretty radical shift in how we see the world, sometimes called a W-field or Gibsonian perspective. The core idea is simple, but honestly profound. Reality isn't smooth, it's not continuous. It's built from these discrete, fundamental elements, we're going to call them tokens, that operate on a huge computational grid.
And this completely reframes the whole project of mathematics. I mean, look at this. The classical slogan says a topos is a universe of sets varying over contexts. It's abstract, right? But now, look at the W-topos slogan. A universe of token-realizable local worlds varying over admissible configuration contexts. The magic words there are token-realizable. This is a huge shift. We're not talking about abstract ideas anymore. We are talking about worlds that can be physically, computationally constructed.
Okay, Section 3, the W-field dictionary. Now this is where things get really exciting for me. We're about to see how this theory isn't just some philosophical hand-waving. No, it is a rigorous, honest-to-goodness program for translating abstract math into real physical processes.
Let's start with something familiar, something we all probably remember from calculus, the classical derivative. You see it in the equation here. It defines change by taking a limit, right, as some tiny little step, h, gets infinitely close to 0. But that whole concept, the idea of an infinitesimal point, it only works if you assume the world is perfectly smooth, that you can just keep zooming in forever.
Now, look at the W-field version. The top part, f of n plus 1 minus f of n, that looks familiar. It's just the change between two discrete steps. Simple enough. But the magic, the whole game changer, is in the denominator. Instead of some abstract limit h going to 0, we have a concrete physical value, t of n. This isn't a limit, it's a real thing. And this one change completely regrounds calculus in a new, discrete reality.
So what is this t of n? It's the token measure. And what it represents is the local physical cost. The actual resources, the time, the computational effort that it takes to make a single step on this lattice. All of a sudden, calculus isn't just about abstract slopes on a curve, it's about the physical cost of change at a specific spot. This makes the math deeply physical and contextual.
And this slide, I think, really illustrates the sheer scope of this project. This is a full-blown dictionary, translating the abstract language of math into the physical language of computation. An abstract site becomes a concrete configuration context lattice. A sheaf becomes a lawful emergence object. Even the system's internal logic gets a new name, the logic of token admissibility. Every single abstract concept is getting a physical, computational counterpart.
Section 4, when truth is realizability. So you can imagine, this translation project has some profound consequences, especially for something as fundamental as the concept of truth itself. In this new system, logic gets physical teeth.
Just look at this translation table. In classical logic, P and Q means both propositions are just abstractly true. Fine. But in the W-topos, it means both constraints can be physically instantiated at the same time. P implies Q means that any physical realization of P must lawfully extend to a realization of Q. Truth is no longer about a true or false value in some abstract table, it's about what can actually physically exist in this token universe.
Section 5. Emergence is sheaf gluing. Okay, this brings us to the intellectual heart of this entire framework. We've established all these local rules for our little tokens, but the big question is, how do these tiny local computations assemble themselves into the vast, coherent, global world that we actually experience?
I mean, this is the fundamental question, right? The one this theory is trying to answer. How do you get from these local, pixel-like rules to a stable, large-scale reality? How does the micro build the macro?
And here it is, the answer, the central thesis in a single powerful sentence. Emergence is sheaf gluing under admissible covers. This is the mathematical engine that connects the low-level token rules to the high-level world we see. So, what does that actually mean?
So what is this gluing? It's a process. You start with countless local token states, all disconnected but compatible with their neighbors. Then, a gluing law comes in and acts like a set of assembly instructions. And the result isn't just any old possible world, it's the single, unique, coherent global reality that emerges from lawfully stitching all of that local information together. The universe isn't a given, it's a render.
Which brings us to our final section, number 6, a new grammar for reality. So what are the ultimate consequences of this new framework, and where does it all go from here?
Well, the implications are just enormous. This isn't just another theory, it's a brand new grammar for building worlds. It gives us a complete mathematical language for discrete physics, and it fundamentally ties the concept of truth to what is physically possible. But maybe most importantly, it bridges that massive gap between low-level rules and high-level emergent structures. And in doing so, it completely detonates that old assumption that Topos theory is just some abstract game for mathematicians. It's a tool for describing how worlds are actually made.
And this final slide just sums up the entire transformation perfectly. The old Topos says sets vary over contexts. The new Topos says worlds vary over token law. This is not just a reinterpretation. It's a bold proposal to rewrite the very code of reality, grounding mathematics not in some abstract Platonic ideals, but in the physical computational process of what can and cannot exist.